let us look to regular consensus algorithm in the fail-stop model when we have perfect failure detectors. So here is our consensus interface. So a process can do a propose some value v and can decide some value v prime, we say. So that's the request event is a propose, and the indication event is a decide. And we have the properties that we just mentioned. So our algorithm uses a perfect failure detector and best ever broadcast. Each process stores its proposal in the state variable proposal, and possibly it can adopt another proposal by changing its proposal value. And it also stores the identity of the last adopted proposer in the last prop state variable. At each process, the algorithm works as follows. So at round I, process PI is the leader. And what it does, it broadcasts the proposal that it has currently, V, and decides on that proposal. Other processes in round I adopts I proposal value, which is V, and remember that the last proposer is I. So it means that other processes waits for the delivery of the broadcast, and in that case they adopt the value and you change the last proposal, or they wait for the crash of process PI. So this is basically the algorithm. You can observe the following, that process PI, after it decides, it has finished its task, it has decided. Second, in round I, all processes between 1 and I minus 1 have finished, as I said, and they finish either by crashing or by deciding and broadcasting a value. So we see here that we are ranking processes from 1 to n, and we are in a phase where processes adopt the value of process ranked I. This means that processes P1 to Pi minus 1 have already finished, so we are talking about processes that have a number I or higher. So the basic idea of this algorithm can be seen as follows. We assume that there is at least one correct process, so there must be a first correct process P. When it becomes a leader, P decides its value and broadcast, best ever broadcast the value. And the best ever broadcast ensures that all correct processes get the value V. This is the validity property of the best ever broadcast. So when each correct process delivers V, each correct process will adopt the value V. So it changes its own value to the value V, and then future round will only propose the value V. This is the basic idea of the algorithm. So let us look to an execution where we might have a problem which is called the orphan message problem. It also illustrates how the algorithm really works. So initially we have P1, P2, P3, and we assume that they have three different proposals. So P1 has A, P2 has B, and P3 has C. So P1 decides on A, and then P1 fails. So in this case, P2 and P3, on their view of rounds, they move to round 2. So in this case, P2 is the leader. He decides on B and then broadcasts the value B. So here, process P3 gets the proposal B and adopts it, and also says that this is the last proposal that I have adopted, and it comes from proposer 2. Now, if the proposal of process P1, when it did a broadcast, was late on delivery, as you can see here, then it should not adopt this proposal, because if it does, then it will decide on the value A. So process P2 and P3 decided on different values. So the point is, you only adopt from a process or node I if I is larger than the last proposal you adopted before. So in this case, this will not be adopted at P3, and P3 will decide on the value B. I think now we have a very clear algorithm. A leader at round R might crash, but much later affects some process at a higher round number. So we always rank processes. P1 is less than P2, less than P3, and so on. And the invariant of this algorithm is to adopt a proposer P if that proposal is ranked higher than the current proposer that you have in the last proposer variable. Otherwise, P must have crashed and should be ignored. And I think you can understand why P must have crashed, because moving to a higher round happens only if a process detects the crash. So let us look to an execution without failure, so we see what happens. P1 decides on A and broadcasts A. P2 now adopts the new value A and say that the last proposer is P1, or 1 in this case. The same thing happens at P3. Each process moves to the next round because it got a broadcast, and it will continue deciding on A, and P3 will adopt this value, but now it's coming from proposer 2. So the last proposer now is 2. And then it will decide on A. So that looks great. So everything is fine. Now let us look at the execution with failure. P1 decides on A and then crashes. But this proposal value arrives at process P3 and it is adopted by process P3. Process P2 detects the crash and moves to the second round. Then it decides on B, which is correct. Process P3 also moves to the next round because it got the value of the broadcast at round 1. And in this case, it adopts the proposal B with the last proposal P2 or 2 in this case. Then it moves to the next round and it decides on B here. So as you see, we have 3 processes. The correct processes decided in B and the failed process decide on A. So it is clear that this algorithm does not support uniform consensus. So what about uniform consensus? So it is not uniform, as you can see here.